Okay, so we shall take up the very interesting topic of cryptographic hash functions today. So we have concluded with stream ciphers and also with understanding about what is meant by pseudo randomness in the last class. So today we will take up a slightly different topic. It's called cryptographic hash functions, and the ideas are quite different from what we have studied till now. Okay, so we will take up this, and in today's class, so it is quite a big topic. So we will divide it into split it into classes. In today's class, we will talk on applications, that is where hash functions are applicable, and then talk about certain security requirements from such kind of hash functions. Okay, and then we will discuss about randomized algorithms, how in order to prove certain aspects of hash functions, and then talk about the relative order of hardness among the requirements. We will talk about like which is easier, which is harder, and try to reflect upon them. Okay. So first, where are hash functions applicable? So hash functions are applicable essentially to provide assurance for data integrity. Okay. So therefore the idea is that suppose you have a hash function which is h and there is x which is some data. Okay. So what the hash does is that so typically the x can be a very big piece of data. Okay. So like normal hash functions, what we study in normal computer science classes, it will take and it will produce a smaller digest of the message. Okay. So this digest, or say if I call it the hashed output, okay, is now compared and seen that whether, so suppose somebody tampers with x and therefore x becomes x dash. The idea is that the person who will verify whether hx and hx dash are same or not. Okay. So obviously you understand that one property of the function h is very important. What is that? It should not be easily invertible. So suppose I know that what is the value of hx. Okay. Suppose I modify that x to x dash, and then suppose because since it's h is a public domain algorithm, anybody can compute hx dash and from there can infer what is the value of x dash, then it will not serve the purpose. Okay. So therefore there are two important things. One of them is this one-wayness, and I will come to the second aspect shortly. So you see that typically x is a large binary string and the digest is a fairly short binary string, say typically 160 bits. Why 160 bits? Also we will see in our as we go ahead. Okay. So as I told you that the applications are like this. Suppose there is you want to ensure the integrity of the data x, then what you do is that you compute y, which is equal to hx, and remember that y has to be stored in some secured place. Okay. So why? Because if x is, so how do you check? Now if x is altered to say x dash, and if we assume that hx and hx dash are not the same, then the alteration of the message is readily caught by verifying that whether y and y dash are same or not. Okay. So where y dash is equal to hx dash. So therefore these type of things are useful in digital signature schemes, message authentication codes and things like that. Okay. So it has got a lot of importance in particularly for the for applications which we heavily rely upon in network security kind of thing. Okay. So slowly you see that we are going into more practical aspects. Okay. So therefore hash functions are quite useful, and essentially one thing to be kept in mind, again I am stressing upon that till now what we have studied is encryption. We have studied symmetric key encryption. Symmetric key encryption was assuring the security of the data or the secrecy of the data. Okay. But hash functions is important to give assurance for the integrity of the data. Okay. So you see that here one thing has to be kept in mind, that the function h, okay, this is a pictographic representation, this h output has to be transferred through a secured channel. Okay. So therefore so you see that data is being transferred through an insecure channel, somebody modifies this value, then what he does is that he computes this h value and checks whether this is equal to this secret value. Okay. So you see that this this verification can be done based upon the assurance that the hx value or the digest has been transferred without change. Okay. So therefore the comparing the digest of data sent over insecure communication channel with securely obtained original digest allows us to verify the integrity of the data. So therefore it gives us assurance for the integrity of the data. So immediately you can understand that with whatever we have studied about symmetric key encryptions or any encryption for that matter, that if I would like to also replace this secured channel by an insecure channel, then can you suggest what we can do? Yeah. So what we can use is we can assume that the sender and the receiver has a shared piece of key. Okay, and then instead of having hx, we will compute hkx. So k is another parameter to that function h. Okay, so therefore there are two classes of hash functions. One kind of hash functions are called unkeyed hash functions, like as it is told here, and the other class is actually something which is called keyed hash functions. Okay, so therefore this is an example of a digital signature. So I think all of us know what is a signature, and also what is, to some respect, what is a digital signature. So there is some data which I would like to send over the insecure channel, but at the same time I would like to also sign this piece of data. Okay, so what I do, I take this, I apply this function or hash function h, but at the same time I sign my data using my private key. Okay, and then I transfer this over the insecure channel. So you see that now any eavesdropper is unable to compute the value of the corresponding signature, is unable to compute the signature, because he or she does not have the private key. Okay, so therefore this is transferred here, and the data. So how do you verify? You take the data, you apply the function h, and then you verify by decrypting using the public key actually. Okay, so we have really not gone into the asymmetric key cipher discussions, but just we can just understand that, I mean, in case of asymmetric key encryption, the private key and the public key are inverses of each other. Okay, so they cancel out kind of. Okay, so therefore you can verify and you can operate. So therefore you see that if you have a keyed hash function, as we have discussed, then you can actually transfer the digest over an insecure channel. Okay, so therefore suppose we also have a key in the computation of the hash function, and this is how it is represented as hkx. Okay, and the key is kept secret. Then Alice and Bob are in this case sharing key, so therefore this can be an example. This is an example of a symmetric key cipher, right? So that because they are sharing the same piece of key. Okay, so Alice and Bob, what it does is that Alice computes y for x using k. So what is y? Y is hkx. Okay, and sends it to Bob. Now Bob receives the value of x dash. Okay, and he computes the value of the hash value, because Bob also knows the corresponding key value, right? And therefore he can compute the corresponding hkx value, right? And if the hash matches, then the message is unaltered, and at the same time it is also guaranteed that the hash value is also transferred, that is neither the hash value nor the message has been tampered. Okay, so note here that y is not required to be kept secret, and I think you easily understand why. Okay, because it's assumed that only the sender and the receiver has got possession of the value of the key. Okay, so now we will come into the definition of hash function. Okay, so we have defined till now what is an encryption function. So how many tuples were there in an encryption function? There are 5 tuples, right? But in this case you see that there are 4 tuples. Why? Because you have an x function, y function, k function and h function. What is missing here is a decryption, because in case of hash you don't require the decryption. Okay, so and it's actually supposed to be one-way function kind of. Okay, so in a hash function typically you can understand that there will be a domain and there will be a corresponding range. So the domain is represented by x and the corresponding range is being denoted by y. There is a key because of the keyed hash function thing which I told you, and there is a algorithm which is the hash algorithm. Okay, so that is h. So here x is a set of possible messages, y is a finite set of possible message digests or authentication tags. Okay, and your k is a k space or the key space, and it's a finite set of possible keys. And what about the function h? H are all possible mappings from x to y. Okay, so therefore you can understand that h essentially is a function from x to y. So how many values of x are there? If I assume that in x there are say m values, okay, and in y, so this is x and this is y, there are say okay, so if you can assume that x is n and y is m, just to keep the notation same. So how many possible mappings are there? Yeah, so for each possible mappings, I mean for each possible input here, there are m possible outputs. So therefore you can apply this and you can see that there are m to the power of n such possible transformations, right. So therefore from there we choose any one function and we denote that function as fxy, okay. So your hash function will be one of them, right. So therefore if you say that your hash function f is a subset of all possible values of fxy, okay, then this is, so therefore this is your something which is called a hash family, and from there you choose one hash function, okay.
Why are we using the subset only?
Yeah, because I am choosing only some of them from there. There are various mappings possible, right. So therefore this is called sometimes also an n comma m hash family, because I am considered with only the transformations from m number of values, n number of values to m number of values, okay. So therefore this is the definition of hash function, and now we will study about the security aspects of hash functions, okay. So there are three important properties which a hash function must satisfy. So the three important hash function properties are pre-image property, second pre-image property, and collision property, okay. So we will study them one by one. So you see that first of all let us take the definition of a pre-image problem. So you can understand from the definition, it says that if there is a hash function which is called h, okay, and you are being provided with the message digest, the problem is to compute the inverse of hx, okay. So given hx, you are trying to compute the value of x which will lead to the same hash value, right, and you can easily understand that this should not be easy to solve. So again, easy means not solvable by an efficient algorithm, okay. So we discussed about what is meant by an efficient algorithm yesterday also. So therefore the idea is that your hash function for which the pre-image cannot be efficiently solved is said to be pre-image resistant, okay. So that is one fundamental property which a hash function must satisfy, a cryptographic hash function must satisfy, okay, because of its application. So this is one important definition. The other one is called second pre-image, okay. So what is a second pre-image? Second pre-image means that suppose you are provided with a value which is, so there is a hash function which is h and there is an element which is x, okay, and now you are supposed to give back another value, say x dash, which is not equal to x but leads to the same message digest, right. So you see that this is slightly different from problem from the previous one. Why? Now in the previous problem you have been provided with a message digest, and from there you have to give back the corresponding input, right, from where the hash function has or the hash output has originated, okay. But in a second pre-image problem, you are being provided with one value of x, and then you have to compute the value of hx, and now you have to go back and you have to find out what is the value of x dash which is not equal to x and which leads to the same hash value, okay. So what is the difference? Where is the difference? So suppose you have an algorithm which solves the pre-image problem, it will not necessarily solve the second pre-image problem. Why? Because in case of pre-image problem, you are just giving the inverse, right, but in a second pre-image problem, if you engage the same algorithm, there is a problem that you can get back x which is equal to the value of x, okay. So although you are able to invert, you are not able to give a different value of x, okay. So the problems are different, you see that, right. So therefore the idea is that if this problem is solved, then again you can generate a valid pair, and therefore you know that you cannot apply it for various applications, okay, like authentication and signatures and things like that, okay. So these are two important problems, but probably the most widely studied problem is known as the collision problem. So the collision problem is, I guess, a little bit more simpler problem. It says that given a hash function, you have to just give result in two values, say x and x dash, which are not the same but which leads to the same hash output. Okay. So therefore, you have been provided with one algorithm, you have to study that algorithm and give two distinct values which results in the same hash output. Okay. So you see, from the attacker's point of view, this is a simpler problem. Okay. But from the designer's point of view, this is a much harder problem to handle. Okay. So intuitively also we see that if I am designing a hash function and if I am able to make it collision resistant, then I should be able to give guarantees for the other properties also. Okay. I am not proving this at this point, but it is quite intuitive. Okay. But we will try to prove this result also. Okay. So therefore, note that if this is solved, then if xy is a valid pair, then so is x dash y, and if not, again in bracket efficiently solvable, then the hash function is called collision resistant. Okay. So these are the three important properties which a hash function must satisfy, right?
Suppose there are two, it is said that if it is not efficiently solvable, then it is okay. But suppose there are two messages and it is we are calculating the same hash value, then also it is a problem basically, because we need that each and every message leads to a unique hash value. Whether it is like,
yeah, but that will never happen, because you see, okay, this is another interesting question. So therefore, you see that in any hash function, typically we have a large x and a small y, right? So therefore, you can never have a one-to-one mapping. Okay. So there will always be collisions, but the only challenge is that from the designer's point of view, the collisions should be hard to find. Okay. So you should not have a very efficient algorithm through which you can calculate the hash value. I mean, two results which will result in the same hashed output. Okay. So therefore, this is a designer's challenge actually. You know that hash functions are quite probable, but at the same time you have to give guarantees that they are not easy to find out. Okay. Therefore, you see that all the good hash functions that we had till now, like MD5 and SHA1 and things like that, I will tell the names in details, but they have all resulted in collisions. Okay. And it's really not so easy to design a hash function.
there is a mention how are they providing security? They are rather providing data integrity.
Yeah.
But hash function never contribute to the security of the message being passed.
No. So we discussed this at the very beginning, that what hash functions are being applicable to is to provide the integrity of the data. That is the main application. Okay. So it's okay. Yes. Okay. So now we will take up one model which is called a random oracle model. It's a slightly theoretical model, but we will take up that. Okay. So random oracle model was originally developed by two people called Mihir Bellard and Phil Rogaway. Okay. So this is a quite theoretical model. It captures the concept of an ideal hash function. So therefore, you can imagine that a random oracle is like this. Like suppose you have a very big book, okay, of random numbers. Okay. What you can do is that you just open any page, and whatever number you get, you return that number. Okay. So you see that if you open the same page again, then you get the same number. But the thing is that each time if you open any arbitrary page, then which you have not opened before, then you get a random number. Okay. So a random oracle model's ideal hash function is modeled exactly in the same way. That is, if you access a value of say x, okay, and which you have not accessed before, then you are returning a random number. But if you are accessing something which you have accessed before, then you are returning the same number which you have returned before. Okay. So if a hash function h is ideal, then the only way to compute the hash of a given value is by actually computing it. That is, even if you know many previous values, then also computing the hash of a new value should not be derivable from the previous things.
Is it mean to say that all the messages are equally probable and independent of each other?
Yeah, exactly. That is, so we come to that. But at the same time, what I am also stressing here is that, I mean, there can be hash functions, okay, which are looking quite ideal, but the thing is that which, I mean probability wise is independent and it's uniform, but still getting maybe say 2-3 values or say some values, you are able to calculate the value of the of something which you have not yet calculated. Okay. So one example you can think, I mean already we have studied such kind of examples. If you have a very linear kind of equation, Okay, so you know that in a linear equation, if you know the output of 2 points, from there you can calculate all the points, right? So for example, this is an example of a non-ideal hash function. Okay, so I hope you can see this. It says that hxy equal to say ax plus by mod n. Okay, so suppose a, b and all these things are not known to me. Okay, but the thing is that if I know the value of hx1 comma y1, that I know is equal to ax1 plus by1, and I also know the value of hx2 comma y2, and that is equal to ax2 plus by2. Okay, from there I am trying to calculate the value of say rx1 plus sx2 mod n and also ry1 plus sy2 mod n. Okay, so you see that these are linear combinations of the previous coordinates. Okay, so you had x1 y1 xy here, I mean x1 y1 here and x2 y2 here, and I am calculating this as a linear combination of x1 and y1, and also this one as a linear combination of y1 and y2. Okay, and I need the hash output. Okay, so you see that this particular input I have not previously computed, right? But from my previous results I can express this value, I can deduce this value. How? And because I know that this output should be equal to r h1 x1 comma y1 plus s of h2 x2 comma y2, and I know this value and I know this value. Okay, so you see that I do not even need the value of a and b, right? I just need to know the value of r and s, which I know. From there I can express my new hash output from the previous hash output. Okay, so this is an example of a non-ideal hash function which I am not defining using the random oracle model, which I am ruling out in the random oracle model. Okay, so random oracle models should be such that although suppose, I mean pictographically this will look like this. Suppose you have got a domain say x, okay, and out of them suppose you take any subset and I call that x naught, and suppose you know all the corresponding hash outputs for this x naught. Okay, so now if you access a point from x difference x naught, so these are difference notation, so that means you are accessing these values. Okay, so then these hashed outputs should not give you any information about the other hashed outputs. Okay, so if you had started, I mean before you have started any computation, what is the probability of any hash output occurring? It is 1 by m, because m is the range size. Okay, but even after computing this x naught, which is a conditional probability actually, your probability still stays 1 by m, right? You are not able to compute with any better probability. Okay. So again, I mean just before going away from this point, that oracle is actually not an algorithm, it is neither a formula. Okay, it is just, you can imagine it as a giant book, as I told you, which will just give you the answer, but you don't know how it's giving the answer. Okay, so if you have seen the Matrix cinema, it's like the oracle that was the future. I mean telling what is the future, but how it was telling the future, no one knows, right? So something like that. So therefore, as we told that we are discussing about the independence theorem, and this is what I have told you in the picture. Okay, so therefore, suppose you take h, which is a belonging to fxy, and this is chosen randomly, and therefore if you know out of them, you just take a subset say x naught, and if you know all the values of the hash in this range, in this x belonging to x naught, then the probability that hx is equal to y is equal to 1 by m for all x which belongs to x difference x naught. Okay, and for all y which belongs to y. So you can note that this is actually a conditional probability, and what it essentially tries to say is that the knowledge of the previous computed values does not give any advantage to the future computations of hx. Okay, so previous values of hx will not help you. Okay, so this assumption in the random oracle model will be used in the complexity proofs that we will do. Okay, so therefore you can keep this in mind. So this independence property and theorem, or other whatever we say, will be useful in my future proofs. Okay, you can't, that is not the objective. You are not doing encryption. So if you remember, the definition was only a forward transformation. Okay, we are not doing an inverse. We don't need an inverse, because we are giving just an assurance of the integrity of data. Okay, Okay. So, therefore, these algorithms in these random oracle models will be essentially randomized algorithms. So, what are randomized algorithms? So, I think you have studied in algorithm class. Okay. So, therefore, I will not go into real details, but the thing is that essentially it will the main thing is that we need essentially is that it will make random choices. Okay. And the class of algorithms that we will study here are called La-Vegas algorithm. Okay. So, La-Vegas algorithm means that they can fail, okay, but if they terminate, then they will be successful. Okay. So, therefore, these class of algorithms can fail, but if they terminate properly, then they will be successful, they are true. Okay. So, therefore, if you get a result out of here, then this algorithm cannot give you a wrong result. It can fail, but it will not give you a wrong result, right. So, again you know that we can do this worst case analysis and average case analysis, okay, but I mean you know this. So, the idea is that if there is a worst case success probability of say epsilon, then what it means is that for every problem instance this randomized algorithm will give you a correct answer and that probability will be at least epsilon. Okay. So, therefore, why is there a probability? Because it can fail sometimes also, right. I mean it can fail sometimes, and when it returns a correct answer, the correctness probability is at least epsilon. Okay. So, in average case you are actually averaging it out, okay, averaging out over all possible function values and also possible inputs of the functions. Okay. So, therefore, over the range of x and y, if x and y are part of your problem instance. So, therefore, these things all of us know, but this is just to mention. So, let us try to understand this first, that suppose there is a random algorithm or randomized algorithm which solves the pre-image problem. Okay. So, what it does is that it's quite a simple algorithm. So, the pre-image problem is that you have a hash function and you have been provided with a y and you are asked to find out x, right. So, what is q here? Q is essentially determines the number of queries that you make. Okay. So, for example, I told you that in a random oracle you can actually ask questions to the random oracle. You can ask as many questions as you want. Okay. So, if you can ask, I mean as many means if you really want to solve it efficiently, you have to ask polynomial number of questions. Okay. So, therefore, if you ask a polynomial number of questions to it, and therefore, from those polynomial questions you have to now give the corresponding answer, that is what is the inverse of y. Okay. So, therefore, again coming back to this diagram, what you are doing is that this is your x naught, right. So, therefore, you are essentially asked, suppose there are k number of values in this x naught, I mean q number of values in this x naught. So, you know all the hash values here. Now, based upon this knowledge, can you say that what is the, suppose this has been hashed to y, what is the corresponding value here? Okay. So, suppose what you do is consider a very simple algorithm. What it will do is that it will choose any x naught which is a subset of x. Okay. So, you see that this is a random choice, right. It can choose any x naught, but only thing is that the cardinality of x naught in this case is q. Okay. For each value of x which belongs to x naught, and what I will do is that I will check that whether hx is equal to y. If hx is equal to y, then I will return x. This can be a simple algorithm, right. So, therefore, you see that what is the probability. So, therefore, if I say that there is an event ei, okay, which means that h of xi is equal to y. So, I can define an event in this way, okay, that is h of xi is equal to y. So, what is the probability that this is true? It is equal to 1 by m. So, therefore, what is the probability that this is not true? It is 1 minus 1 by m. So, the probability that ei fails or ei is not true is actually equal to 1 minus 1 by m. Okay. Now, from my independence theorem, for all the q queries, if they fail, then essentially the probability of failing will be 1 minus 1 by m whole to the power of q. Okay. And then if I have to be successful, then it will be 1 minus that value, right. So, therefore, the probability that in the average case that the success probability in this case will be 1 minus 1 by m whole power q, 1 minus 1 by m whole power q. Okay. So, this is quite straightforward. Okay. So, what about the second pre-image problem? So, in a second pre-image problem, the problem is that you have been provided with the function h and you have been given the value of x, and from there you have to give the second pre-image, which means that you have to give an x dash which is not equal to x, but which results in the same hash output. Okay. So, then what you do is that you the first step will obviously will be to calculate the value of hx. Okay. So, you calculate the value of hx and then you choose a value, I mean a subset x naught excluding the value of x, of course, right. So, you choose any other subset and therefore, the size of mod x naught is suppose q minus 1, okay, and then you repeat the same process. That means, you see that whether hx naught is equal to y, and if this is so, then you are returning x naught. Okay. So, therefore, through this what you have ensured is that x naught is never equal to x, right, and therefore, you see that this is also an example of a La Vegas algorithm, right, because it will not give you a wrong result, it will not give you an same x output, right. It will give, if it gives you a correct answer, it will give you a true answer. I mean, if it gives you an answer, it will be true, right. And what is the probability? Similarly, you can do this calculation and it will come to 1 minus 1 by m whole power q minus 1, because you are making q minus 1 queries here, right. And how many queries have you made? How many queries have you made to the hash function? You have made q queries, and therefore, this is actually q. Okay. So, therefore, often this class of algorithms are being represented like this, that is epsilon comma q. So, epsilon stands for the average, I mean for the lower bound of the probability, and q stands for the number of queries that you make. Okay. So, in this case, epsilon will be equal to 1 minus 1 by m to the power of q minus 1, and the number of queries that you make will be q, right.
Why are we considering only the subset of the message space?
Because that was my definition of an ideal hash function. So, I am using that fact actually. If I make all the queries, as I told you, now I have to make polynomial number of questions. Okay. So, therefore, I am assuming that I have made say some polynomial number of questions. Based upon that, what is the probability of my success? Yeah, I mean, suppose you have got say, so okay, so let us consider figures. So, suppose you have a function h which operates upon say suppose 512 bits. Okay. So, how many possible inputs are there? 2 to the power of 512. So, obviously, if you make 2 to the power of 512 values access, then it will not help, right. You can never finish this in your life, right. So, therefore, so you have to do, I mean, in some small number of values, okay, and still say what is the still able to be able to figure out what is the collision or whatever. So, therefore, these two problems are quite simple in this sense, I mean, till this part. But actually, we have studied two problems. We have studied the pre-image problem and the second pre-image problem. So, what about the collision problem? So, the algorithm to find collision, okay, so we will study this next. So, it says that, so you know that in a find collision problem, you do not have any other thing, but you have only the hash function and you are just told to solve the problem in say q queries, okay. So, you see that what you do first is that you choose any x naught which is a subset of x, okay, and the size of x naught is in this case again q. So, what you do is that from this you access all the values from x naught and you know what is the corresponding values of yx for all the values. So, you compute the hash values for all the elements of x naught, okay, and now you check whether there are some equalities, that is whether there are two distinct values which results in the same hashed output. So, what you do is like this, that is you have suppose x naught, okay, and this is your x, and inside all these values. So, how many values are there? There are q values here, right. So, for all these q values you compute the hashed outputs, okay, and now you see that whether there are two values which are same, okay. So, you can engage some sorting technique and then from there you can search. So, therefore, you can do that as efficiently as you can, Okay, but the thing is that you can essentially what you are doing is that you are trying to determine whether there are two values, say yx and yx dash, okay, which are essentially same for different x dash values. Okay. So what is the probability of this being true? So you see that, again let us see that what is the probability of this not being true. Okay. So that means that suppose you have got q values, and what you are essentially trying is that none of them are equal. So the first you can choose in, obviously it will be some, you can choose in any way, so the probability is 1, and because of the independence theorem I can multiply. Okay, so therefore the next element's probability will be 1 minus 1 by m, because this has to be distinct from the previous one. Okay, what about the next one? It will be 1 minus 2 by m. Okay, and similarly you can continue till 1 minus q minus 1 by m. So why can you do, so therefore you can do this because of this independence theorem, that the assumption that we had for ideal hash functions. Okay, so now does this remind you of something? The birthday paradox, right? So therefore you see that if q is approximately of the order of square root of m, you should be able to find out a collision. Okay, so I think I've already told you the further deductions, I'm not going into them, so that you can follow from the previous class. And I mean you can actually approximate this. So the, no, 23 is only for m and m is some value. Okay, so you can actually approximate this by a value, say e to the power of minus k by m, where k runs from 1 to q minus 1, right? And then you can actually write this as e to the power of minus sigma k equal to 1 to q minus 1, and so m is here and k is here. So you see that it is roughly equal to e to the power of minus k square by m. Okay, so the probability of actually finding out a collision will be, q square minus m. So it will be 1 minus e to the power of minus q square by m, and that if I roughly make it 0.5, then I know that k is roughly of the, I mean rather q is roughly of the order of square root of m. Okay, so now you see that what value of m would you like? For example, if the value of m was say a 40-bit number, so in that case m would be 2 power of 40. So what is square root of m? It is 2 power of 20. So therefore if you do 2 power of 20 searches, which is maybe some which you can really do in using today's technology, so therefore it will not help you, right? So therefore typically you will like that the m value should be high. So therefore if I use as a thumb rule that 2 power of 80 is something which I cannot really do in today's world, then I will keep the value of m to be, I mean, equal to 2 power of 160. So the bit size that I will maintain will be of 160 bits. So that digest will be of 160 bits. Okay, so therefore this is only to prevent this birthday paradox to work. Okay, so the rest of the things you understand. So therefore finally your algorithm that you say will be a half comma o square root of m, because half is your probability of success and the number of queries that you make is roughly of the order of square root of m, right? So is it okay? So now we will start with this topic of comparison of the security criterions. That is, what we have seen is, we have seen the we will essentially consider two important reductions. So therefore we will engage some reduction techniques to understand the relative ordering of the hardness of the problems. Okay, so you see that I will state this fact that solving collision, this we can understand from intuition also, should be easier than solving the pre-image or the second pre-image problem. And the question is, can we reduce one problem to the other? Okay, so we will study two important reductions. One is the collision to the second pre-image problem, and the other one is collision to the pre-image problem. Okay, so what is this proof method? Suppose we are considering this case of reducing collision to pre-image. Okay, so again we will fall back to our algorithm class, and what we will do is like this. That is, suppose I want to reduce my collision to a pre-image problem. Okay, so suppose I assume that the pre-image problem can be solved. Okay. So, therefore, I can write in notation terms like suppose not pre-image problem. Okay. So, I am saying meaning to say that the pre-image problem is not hard. Okay. There is some good algorithm which can solve it actually. Okay. And I can show, if I show that this implies that collision is actually also solvable, right, then this is safe as saying that collision implies pre-image. So, that means that resistance against collision will also imply resistance against pre-image problem, right. So, from there you can understand that the hardness of the collision problem, yeah, so you can follow that, right. So, therefore you can relatively order the hardness, and what you can say is that if you can show a guarantee against this collision problem, then you are also guaranteeing against the pre-image problem. Okay, when I am saying guarantee means resistance. Okay, so therefore, now coming back to this, therefore resistance against collision will in that case imply that it is also resistance against the pre-image problem. Okay, so similarly I can show the other ones also. So therefore, you will find that in most of the research works on hash functions, people try to show that there is a collision first. Okay, because of two reasons. One is because collision is easier than the pre-image or the second pre-image problem, and the second thing is that from the designer's point of view, if you can find out a collision, or rather if you can show that there is no collision, then I can show I can imply that pre-image and second pre-image problem are also harder, right. So therefore, consider this simple collision reduction, that is the collision to the second pre-image problem. So it says that what is this, that suppose you imagine that a second pre-image problem can be solved. Okay, so that means that given a value of x, I am returning a value of x dash which results in the same, which is not. So therefore, since this is also a La Vega algorithm, so definitely x and x dash are not the same, right, and therefore and also at the same time they result in the same hash output. So what I can do is that I can straight away return x comma x dash. So you see that in this case, if your second pre-image oracle is actually an epsilon comma q algorithm, okay, then your collision to second pre-image problem is also an epsilon comma q La Vega problem algorithm. Okay, so therefore using the same q number of queries, because you have not made any extra query here, and with the same probability you can actually solve the collision problem also. Okay, so this shows that your collision resistance implies pre-image resistance. Okay, implies second pre-image resistance, right.
So it should be if collision H from X.
Which one?
So if you
If
it should have been collision H from X, because we are using the solution of the collision problem to solve the
yeah. So okay. So you see that the idea is this, that is the oracle second pre-image algorithm is being given an input of the hash function, and it is given an input of the x function, and this algorithm returns you back an x dash. Okay. So whatever value you get here, you are actually using that to return the corresponding answer. So in that case, actually this if statement really does not make sense. Okay. So therefore this if was probably because in Stinson's version that you have with you, that is the second edition, there is an extra check kept over here which checks that x and x dash are equal or not. But the thing is that x and x dash will always be different, because this is assumed to be a La Vega algorithm. Okay, so I have removed that actually, but the thing is that the if also should be removed in that case. Okay, so the idea is this, that is the oracle second pre-image algorithm is being given an input of h and x. Okay, and it returns you back x dash, and if whatever since whatever value you get here as x dash is not same as that of x, you are returning back x comma x dash. Okay, so therefore since it is a La Vega algorithm, it will give an answer I mean if it gives an answer, it will be correct answer, and thus x and x dash are not the same, I mean not the same, and hx dash is equal, are equal. So therefore collision is also found. So therefore if you can solve the second pre-image problem, then you can also solve the collision problem.
So in this case, you should get the security of the pre-image problem, not the collision, because if you can solve the pre-image, second pre-image,
Yeah.
you can get the value of collision.
Yeah, so the idea is this, that is what you are essentially implying is that the resistance against collision attacks will imply resistance against second pre-image problem. Okay. So from my designer's point of view, I am trying to understand which problem will I address first. So from the between collision and second pre-image, I will try to give certificate against collision attacks. Okay. If I am able to certify that you cannot do a collision attack easily, okay, then I am quite safe that okay, second pre-image problem is also studied that way. Okay. So let us study the other reduction. This is slightly complex. Okay. So therefore collision to pre-image. So therefore you see that in this case, what is the difference? That is, the difference is that so the problem is that I need a collision for a value x. So I choose an x at random, and then I compute the corresponding hash value, that is hx, and the oracle pre-image is then asked h comma y. So that means y is asked as a question, and it returns you back an x dash. But there is a chance that this x and this x dash are the same, because this algorithm does not give you any guarantee for that, right? So therefore you have to do this check. Okay. So now you understand why the if was there actually. Okay. So anyway, so therefore now you check this, that x dash and x are same or not. Okay, and then you return x comma x dash, otherwise it fails. Okay. So this is an algorithm, and this algorithm is assumed that the oracle pre-image is a 1 comma q La Vega algorithm. Okay, and then if you make some assumptions on the size of x and y, which are actually quite practically true, that is mod x is greater than twice that of mod y, then you can show this particular result. Okay. So the result says that suppose there is an h which is an hash function where mod x and mod y are finite, and mod x is greater than or equal to 2 mod y, then suppose the oracle pre-image is a 1 comma q algorithm for pre-image for the fixed hash function h, then collision to pre-image is actually a half comma q plus 1 algorithm for collision for a fixed hash function, which means that the probability of success will be half, and q plus 1 is the number of queries that you make. So number of queries being q plus 1, you can easily understand, because if this algorithm makes q queries, then you have actually made q plus 1 queries here.
So this oracle pre-image will be a randomized algorithm.
Oracle pre-image algorithm is also a randomized La Vega algorithm. Yeah.
Okay. So in suppose in first case it returns a value of x dash which is equal to x, and in another run it returns a value of x dash which is not equal to x. So this reduction proper? Like one run of oracle pre-image might not give you the result. Like
No. See, I mean, so until and unless you get this, you keep on continuing. So whenever, okay, so we have, I will give you the probability proof. So I think it will be clear from that actually. So the idea is that whenever this algorithm can fail, no doubt, but when it gives you an answer, it will give you a correct answer, right? So but we will not do this proof in today's class. We will take up the proof in the next class. Okay. So we will actually take up the proof in the next class, and we will also start with the construction based on this hash function, something which is called a Markel-Damgard construction from the next class. Okay.